Alright, so we're going to look at finding the antiderivative of exponential functions of base other than e. So we're going to take a look at first taking the derivative of 4 to the x power. And when we took the derivative, we had ln of 4 times 4 to the x. And so what the antiderivative is going to do is it's going to be something real similar to that. But instead of dividing, I'm sorry, I'm giving it away. Instead of multiplying by a natural log of 4, we're actually going to divide by a natural log of 4. And then we'll check to make sure it looks okay. Alright, so if I want to take the antiderivative of 4 to the x dx, I'm claiming that it's 4 to the x over ln of 4 plus the constant of integration. Now, if you don't believe me, we'll take the derivative of that and make sure that's actually equal to the integrand. So 4 to the x over ln of 4. Remember, ln of 4 is just a constant, so it's just going to hang out, plus constant of integration. Okay, so when I take the derivative of 4 to the x, it's going to be ln of 4 times 4 to the x, divided by ln of 4, and the constant of integration is all gone. And what we're left with is 4 to the x. So it is equal to the original integrand. And so it follows what a antiderivative is. An antiderivative is something that if I take the derivative of, I get back to the original function. Okay. So in general, if I have if I want to take the integral of a to the x dx, it's going to be a to the x divided by natural log of the base plus constant of integration. And we're just going to kind of work our way through a couple of problems, and we'll have all our usual tricks at our disposal. We'll have u substitution, and all our other little integral rules that we already know. So let's say we want to integrate x to the fifth plus 4x dx, and alright, so don't get creative. You know how to do x to the fifth. Add 1 to the exponent, divide by your new exponent. So antiderivative of x to the fifth is 1/6 x to the sixth plus 4x divided by ln of 4 plus your constant of integration. Alright? And then if I really wanted to, I could take the derivative of this, and then it would get right back to x to the fifth plus 4x. Okay. Let's try something else. Let's do 2x plus 6 and then times 5 raised to the x plus 3 squared dx. And then, I'm going to try my usual tricks. Maybe I let u equal x plus 3, then the du would be equal to dx, and, well, that doesn't look real productive. Maybe I can replace, not replace, but solve, and I'd have u minus 3 equals x, and then I could substitute that in there, and, well, I would have something. I'd have some u plus some garbage, and then 5 to the u, and I'm still kind of stuck with that. I don't know what that is, so we're going to go ahead and do a little exploring, and, well, what if I FOIL out that exponent and see what that gives me? Because I'm kind of looking at that right now, because right now my original u substitution doesn't look real productive. So what we'll do is we'll FOIL out that exponent. Remember, it's a perfect trinomial squared, so don't forget that 6x when you FOIL. Alright, this is looking a little bit more promising. Now I have a quadratic. Derivative of quadratic is a linear, so that's looking good to me. And so we'll let u equal x squared plus 6x plus 9. Du will be 2x plus 6, and oh, look at that. We have a winner. So we're going to go ahead and replace. So the 2x plus 6 and the dx is all replaced. The u replaces the exponent, so we are in good shape. Very good shape. So what's all left is 5u du. You know how to do that. It's going to be 5 to the u divided by ln of the base of ln of 5 plus constant of integration. And then we would like to replace the letter u with what it was originally equal to. Okay, since I like to be efficient and write less, u was x squared plus 6x plus 9. Well, that's the same thing as x plus 3 quantity squared. So we have 5 to the x plus 3 quantity squared divided by ln of 5 plus c. And then you can take the derivative of that and then see if you get back to the original integrand. And you will. You will. It'll be a little bit of work. Not too much, though. Okay. Let's look at maybe one more example. So let's say we want to take the antiderivative of not e, 3 cosine x times sine x dx. And I'm already kind of eyeballing the exponent there as kind of my composite. So that might be what I want my u to be. And also I noticed that, derivative sine and cosine are related. So we'll let u equal cosine x. Then du will equal negative sine x dx. So we're just off by a pesky little minus sign. That's alright. We'll just factor it out of our integral. So it'll be minus integral of e to the u du, and we're in good shape. So it'll be negative 3 to the u divided by ln of the base, ln of 3, plus constant of integration. And then we'll go ahead and substitute back in. So we have negative 3 to the cosine x, ln of 3, plus c. And there you have it. So there is integrating with bases other than e.